So in this video, we'll be going over some of the probability material for the math certification exam. And I'm going to chop this up into 5-minute segments, then have you take little breaks during this. We're going to start with some basic probability concepts in this set. We'll be dealing with sample sizes and events in this set of notes, and then moving on to these other topics. So first, let's think about a very simple experiment. We can flip a coin, and when we flip a coin, we have two possible outcomes. So we can either get a heads or a tails. We can denote these by a capital H and a capital T. When we have a collection of possible outcomes, this defines an event, okay? So here an event it really is just an outcome because we have such a simple probability experiment, but the difference is, I might say, the event is getting a heads, maybe, then you win the game. So I define it within those curly brackets to denote it's a event within a sample space. And a sample space, speaking of, is actually all of those possible outcomes. So again, since this is a really simple kind of event or probability experiment, our sample space is just H and T. That's all that can happen when you flip a coin. You don't get 5. You just get a heads or a tails. Okay, so here's a really simple example. Notice here, it's easy to count the size of that sample space. It's just 2, because at each flip of a coin we have 2 possible outcomes. So let's make it a little bit more complex. We could flip a coin 3 times. And when we flip a coin 3 times, let's think about an outcome. Okay? Well, one outcome could be heads, heads, heads. And maybe you win the game if you get either a heads, 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 or a tails, tails, tails. So we could define that by putting around some curly brackets and call that an event, W, which means I win the game. But let's be more exhaustive and think about what our whole sample space would be, because this is just 2 possible events out of the sample space. So we could get those winning cases. Or we could just get 1 heads, 2 tails. But notice, we don't have to get a heads in that first position. It could be in the second. Or it could be in the third. We could get, let's see, 1 tail and 2 heads, which the tail could be in the first, the second, or the third. And notice the size of this set. I like to always think about the size of the set because it helps us review our counting rules too. So at each flip of the coin, we have 2 possible outcomes, heads or tails. But we're going to flip that coin 3 times. So we use that multiplication rule to say the size of the set is 8. Notice you can actually count it here quite easily and confirm, yeah, it's really 8. Okay? When they talk about compound events, by the way, this is an example where we do have compound events, because a simple event could just be a heads and a tails. Compound would be a combination of heads and tails like we see in this sample space. All right, so now stop. There's a handout to help you practice defining some sample spaces and events. They're a little harder than the ones I go over here, but I do provide a solution with a video solution as well. Okay, in this part of the review, we're going to be going over some counting rules. I go over the 2 major counting rules that I've seen on the exam and that are emphasized in the exam as far as I can tell. And for both of these, you really need a common context about thinking about the number of items or subjects and then the number of items or subjects being selected. So a permutation is the first one we're going to go over, and you want to think about it as being interpreted as the first k numbers of n. So let me provide a real-world context to kind of help us understand what a permutation is really all about. Let's think about, you have a class with n equal 10 students. Okay, and for those n equal 10 students, you're going to select k either equal to 3 to take care of the class pets. Now the thing about your class, is there is definitely a hierarchy of pets. The first pet everybody loves. It's a rabbit. Very cute, fluffy. We like fluffy, cute things. Okay. Second one, it's a frog. It's okay, but some people are a little turned off by amphibians. Okay. Third one, it's a cockroach. Okay. Most people really don't want to be taking care of this. Okay. So you kind of got a natural ranking where when you select those 3 students, there's going to be like a first prize, you get the rabbit, second prize, you get the frog, third prize, you get a cockroach. Okay. So for a permutation rule, what you want to do, often a little notation here. Okay. When we talk about permutations, we often have some sort of way of denoting that, I guess is the best way to say it. And sometimes you'll see that, although some books don't even try to denote it, they just write out this. Okay, where that's n factorial over n minus k factorial. So here, n is our number of students. Okay, so this will be 10 minus the number that gets selected to take care of one of the class pets. Oops, I need to erase here. I didn't leave enough room for the denominator. So let me take care of that. So actually 10 factorial on the top, I started with the denominator, over 10 minus 3 factorial. So notice we can write this as actually 10 factorial over 7. Let me show you a little trick for computing. If you just have a simple, cheap calculator, all you really need to do is compute 10 times 9 times 8 because the 7 factorial cancels out all the other remaining terms in that numerator. Okay, so that we've got now, whoops, there we go, 720 possible ways that that teacher could pick the 3 people to take care of the pets. Notice now here that order is important. I always point that out to students. Order is important, or order matters when you're talking permutation. There's some sort of natural ranking going on here, okay? Versus in a combination. So again, the same context. 10 students. Okay, so we've got the 10 students. We've got the K equal 3 pets, but now they're just all frogs, so who cares which one you get, okay? Now what a combination does is it says ordering's not important. So we still have that n factorial in the numerator, and we still have the n minus k factorial in the denominator, but we say order doesn't matter, so the order in which those, say in this case 3 pets, get assigned to the students doesn't matter, so we divide by, in this case, 3 factorial to take out the distinctiveness of the elements in the ordering. Another way to write that is n choose k. Okay, so here with our 10 students and 3 pets, we'd end up with 10 times 9 times 8, which was our 720, divided by 6, which is our 3 factorial, which will be 120 ways you can assign those 3 students to take care of the 3 frogs in the class. So I ran out of time on that first part of the video, but on this I would like to point out here that the way to interpret a combination is that it's all the ways that you can pick these k items from n when order's not important. So again, I want to just point out, unlike a permutation here, order is unimportant. Order is not important. And that, again, is the way to kind of clear up your thinking if you're trying to decide between, should I use the combination rule or the permutation rule here? Okay, so let's practice that right now. Here's a scenario. You have 30 students in your class, and you need to select some hall monitors. You need to have 3 students in your class serve as a hall monitor. And how many ways can you select your 3 students if, and here's the ifs, each student serves in the same role, Okay, so they're equivalent hall monitor roles. Or if the first student serves in September, the second in October, and the third in November. So now we've got some kind of distinction between the three hall monitors. Okay, so what you really want to be thinking of is the order of the students going to matter? For example, you could select George, Melissa, and Jorge. If each student has the same role, it doesn't matter if you select George, Melissa, and Jorge, or Melissa, George, then Jorge. It still is the same three students serving in the same positions or roles. Okay? So here, you're going to want to recognize that order does not matter. So which rule do we use when order doesn't matter? It would be that combination rule here. So with n being 30 and k being 3, we would simply do that. This is a large number, so I'm not going to worry about working it out. I'll lay out the formula, though, for you. Okay? Really, you want to just think about how this then is different than the next one, where you have maybe if George gets selected first, he's the September hall monitor. Then if Melissa gets selected second, she's the October hall monitor, and then Jorge is the November hall monitor. Okay, so here order does matter. And so we want to be using that permutation rule, which in this case would be 30 factorial over 27 factorial. So notice again the distinction, we're not dividing by that 3 factorial because order does matter here, so we have more possible combinations because George, then Melissa, then Jorge is distinct from Melissa, then George, then Jorge, even though it's the same set of students. So we're moving on in the video to thinking about simulation as it relates to probability experiments. It's recently occurred to me, and I've recently come across evidence that there are misunderstandings about what we mean in probability and statistics to the phrase in the long run and other associated type phrases. So I want to talk about that a little bit. And in order to talk about that, I want you to consider flipping a coin many, many times. So you either get a heads or a tails. If it's a fair coin, meaning it's not weighted one way or another, we expect to get a head about half the time. Okay? And so, for example, I want you to think about what kind of plot, if we plotted something like this. Let me sketch out a very crude idea of the plot here. I'll label the y-axis in a bit. Right now I'll just label the x-axis. We always label our axes, right? Or else we don't know what we're plotting. The number of flips is the x-axis. So maybe on that first flip, you get a head. Okay, you have equal probability also of getting a tail, but let's just say you get a head. I'm going to denote it on the plot as being a 1 for a head and a 0 for a tail. Okay, so maybe for that very first flip, we're up here at 1. Our proportion of heads from one flip is 1 because we had one flip and one head. Okay, then on that second flip, we get a tail. Okay, so instantly we need to think about proportions of heads versus tails. And on that second flip, which is, I'm going to just plot right there, our proportion would now be 0.5 because it would be one head out of 2 trials. So it's 1 over 2 or 0.5. Okay, now let's draw on a reference line for 0.5. Okay. As we go on and get more and more flips, we're going to see some variation. We're not always going to hit 0.5 exactly. We happen to be 0.5 here, but we might see some variation. And at first that variation might be a little extreme, but then it'll tend to level out and get closer and closer to 0.5 as the number of flips gets larger and larger and larger here. So this is what we mean by in the long run. If you perform an experiment over a long period of time, what do we expect to happen? And in the case of flipping a fair coin, we expect to get roughly the same proportion of heads as tails. So our proportion of heads in this case would be very, very, very close to 0.5. Okay, here's actually from our computer simulation I wrote. Okay, so we can see this really does happen. This computer simulation really mimics flipping a coin many, many times. I did it up to 1,000 times. Who wants to flip a coin 1,000 times? I don't, and so I let computers do it. Okay, I want you to think about this because there are going to be test questions potentially that ask you about what happens in the long run. Now, some misconceptions that students have about that is they think it means what's going to be the outcome that happens most quickly in terms of, oh, which one do I think is going to happen first or in the outset of the experiment. And that's not at all what they mean. They mean if you were to perform that experiment over and over and over, theoretically infinitely many times, what would be the, say, proportion of heads and tails or the proportion of outcomes on the roll of a die or whatever the probability experiment is. So hopefully that clarifies a bit.